Hi there. Today we'll look at playing Atari with deep reinforcement learning by Vladimir Mny et al. Of DeepMind. So this is another one of our series of impactful past papers. This paper right here kicked off an entire revolution in reinforcement learning. Specifically, it sort of started the deep reinforcement learning hype. Before that, reinforcement learning was kind of this weird field of Markov decision processes and so on. Now, I know there were successes and all, and stuff was happening, but this really made a lot of waves because it brought the power of deep neural networks to reinforcement learning. And with a pretty simple application of convolutional networks, managed to solve these reinforcement learning games where previous algorithms really couldn't either, or were heavily reliant on hand-engineered features. So we'll take a look here and what people did back then, what was the state of the art, and what they are telling us about that, and kind of set it in relation to today. All right, if you do like papers like this, commentary like this, share it out, leave a like, and tell me in the comments what you think. So let's dive in. They say, we present the first deep learning model to successfully learn control policies directly from high-dimensional sensory input using reinforcement learning. The model is a convolutional neural network trained with a variant of Q-learning, whose input is raw pixels and whose output is a value function estimating future rewards. We apply our method to 7 Atari 2600 games from the arcade learning environment with no adjustment of the architecture or learning algorithm. We find that it outperforms all approaches on 6 of the games and surpasses a human expert on 3 of them. So there's a lot packed into this. First of all, I wanted to recognize the absolute LaTeX savagery right here and here. Yeah. You know, it's just something. I'm not OCD about that kind of stuff. I think we should ditch LaTeX, honestly. But so there's a lot of information packed in this abstract right here. So they say this is the first deep learning model to learn control policies. So that's the task of these reinforcement learning algorithms directly from high dimensional sensory input using reinforcement learning. So what do they mean? This arcade learning environment, if you don't know what it is, it's basically these old games right here. You can kind of emulate them and run them, and the inputs are always sort of the same. So you have one joystick, I believe. So you have kind of this joystick, and it can go into various directions like left, right, up, down, and then also the intermediate directions. And then you have I think also a button that you can push. And that gives you a total of somewhere around 16 or 20 actions in each of the games. So the good thing about this environment is that the actions are always the same, but of course they mean different things in different games. So the games here, for example, Pong or this Breakout, these games are kind of really low pixel games, as you can see, and they come in form of an image, right? So this is an image. This is like 180 pixels, and this is like 150 pixels. And the task here is to learn a policy, which means which buttons and directions you need to push, depending on the observation right here, these pixels, and achieve the maximum amount of reward. So reward is given in each game differently as well. For example, in this Pong game, the reward is every time you score kind of a goal against your opponent. In Breakout, you get a reward every time you manage to hit or kill one of these blocks and so on. So reward is different, but your objective is always to maximize the reward. In a formal framework, you have an agent and an environment. And the environment would always give you an observation, which in this case, the observation is one of these images. And the agent will give back an action. So the action in this case would be which button to press or which direction to move the joystick into. And then the environment would give back a reward. So the reward could be, it could be this, you scored a goal, so that's 0 most of the time, and sometimes it's 1 or 9, or it could be like how long you're alive and so on. This is very, very variable. So the difficulty of reinforcement learning very often is that these episodes can go for a while. So this whole process here will repeat over time, and this can go on for hundreds of steps or thousands of steps until you're done, playing a game like this right here. And the reward can be very sparse. So you might only get a reward at the very end of the game. Sometimes, most often in these games, you get one in between, but still there can be multiple time steps where you don't have a reward. And your task is to figure out which of the actions were the good ones. This is known as the credit assignment problem. And to do the credit assignment problem just from pixels alone, that was unheard of at the time this paper came out. That's why they say we are the first deep learning model to successfully learn directly from high-dimensional sensory input. Okay, so the power of deep learning, they argue, is that a deep neural network, a convolutional neural network, can extract these high-level features by itself. However, at this time, people only knew that it could do so for supervised learning. Basically, for every input of an image, you had a label, and that's how you train these convolutional neural network. Here, it's very different. Here, you'll get maybe 1,000 of those images, and you'll simply say, well, you got a score of 1,100. And somehow you need to figure out which ones of these were the ones that gave you the good score, and how to generalize that. So there are various difficulties here to apply convolutional neural networks to this problem, and they have detail right here how they did it. So they say the model is a convolutional neural network, which have been demonstrated. So this is after things like AlexNet, though before ResNet, trained with a variant of Q-learning, whose input is raw pixels and whose output is a value function estimating the future. So we'll get into Q-learning. Q-learning is a reinforcement learning algorithm that has been around, for a long time, but just not combined with deep neural networks. And then they say the last cool thing here is that they apply them to 7 games with no adjustment of the architecture or learning algorithm. So they apply the same algorithm, the same hyperparameters to all of the 7 games, and the model learns all of the 7 games, not as a single model, but as 7 different models. However, they all have the same hyperparameters, so they don't need to tune them, which is an additional benefit. Like, this would have been a cool paper even if they had to sort of tune the algorithm to each of the 7 games, but they didn't, which makes it even more impressive. It's kind of their point here that this deep reinforcement learning can be some sort of a general learning mechanism. Of course, later there has been like giant amount of development since this, and people have come up with all kinds of giant architectures and whatever corrections of policy corrections, sim to real, continuous control. This is most of it is a derivation of this work right here. And this work, it reads surprisingly simple, I have to say. And it's almost like they had little idea what problems were to be tackled later in RL, because it kind of reads like, we have this thing and it can learn general things. So we're still not done with reinforcement learning. I guess we've just started. Okay, so in a bit more formal setting, what you'll have in reinforcement learning are these rewards, right? So at each time step, you perform an action, you're in a state. So we said you get back an observation, and we call the observation the state. Now, these two things aren't entirely the same thing. So the observation is what you get back directly from the environment, and then the state, it can be something more. Like if you remember something from the last observation, that can be part of your state. The state is basically what you base your decision on, and the observation is the pure thing you get from the environment. Now, in this case, they do some processing, but essentially will regard them as the same thing. So the state is what you see of the environment. Then in each of these steps, you perform an action. We'll call that this A thing right here. And in each step, you also get a reward for the last action that you took. And the reward is going to be lowercase r. Now, what you want to do formally is you want to maximize the reward that you get in time t. Sorry, that's the reward you get at time t prime. What you want to do, if you play an episode, you're here and you perform an action, you go here, you perform an action, you go here, you perform an action, you go here, and then your episode is done. For each action, you'll get a reward. Reward 1, reward 2, reward 3. What you want to do is you want to maximize the total, the sum of all of these rewards. So over the course of your episode, you want to collect as much reward as you can. Now, there is a discount factor right here, which is sort of saying that rewards that are very far in the future, they're not as important as rewards right now. However, you can set this to 1 if you want. So you see, you want to maximize the sum of future rewards, which is this thing right here. Okay? So how do you do this? There are two main methods in reinforcement learning. The first one is called a policy gradient method. And very briefly, a policy, we'll call it pi, takes in a state, S, and it gives you back an action, okay? And I mean, this is the same for Q-learning, but in a policy gradient method, which is not this paper, but is like a little bit easier to understand, I believe, we'll simply say, well, we'll simply train a neural network to do that, right? And there is this policy gradient trick where you can backpropagate even though the reward isn't backpropagatable and so on. You can simply say we'll learn a neural network to give us the action that's best, right? So we'll have a neural network, the state goes in, neural network, and then we'll just have as many outputs as there are actions, like action 1, action 2, action 3, action 4, and we'll treat it as a classification problem, right? So you simply train the network to pick the action that is best in this case, and irregardless of how you know which action is best right now. In Q-learning, you do something else. Namely, you train this thing called the Q function. The Q function is a function that takes in a state and an action, and it gives you what the reward is going to be in the future if you are in this state and perform this action. Okay, so you are in a given state, right? And you have 3 actions at your proposal. Okay, you have action 1, action 2, and action 3, and you are in state S. What you would do is you would call the Q function. If you had a perfect Q function, it could give you the reward. You would call the Q function 3 times. You would call the Q function first with A1. You could say, what's Q of S and A1? And the Q function would maybe say that's 7. And here you say, what's the Q function of S and A2? And it would maybe say that's 4. And here the same thing for A3, and it maybe say that's 1. Then you would know, aha, if I take action 1, my reward from not only the reward for this step, but my reward from here on until the end of the episode is going to be 7. That is if you had a perfect Q function. Now the Q function is always, of course, conditioned on a policy right here. So there's what it basically says, if I take action A1 right now, and after that I follow policy pi, then I'm going to get the reward of 7. It's a bit of a multi-layered reasoning approach, but ultimately you don't have to worry much about this being conditioned on a policy. Ultimately, the Q function says if you take this action right now, what will the reward be for the entire rest of the episode. Okay, so if you had a perfect Q function, you could simply ask it about all the actions as we did here, and then pick the action with the highest number. Okay, and then you're guaranteed, because there could be a situation where your reward in a single step is going to be very high here, like 100, and here 0, 0. Okay, and you would be tempted to take that action right here, but after that it's just going to be 0, 0, 0, so your total reward is going to be 100. But here, even though it's 0 now, it could be that after that it's 50, and then 40, and then 2000, and so on. So your total reward is going to be much, much more. If you were simply to train a function that tell you what's the reward in the next step, then you would lose, because that function would not be able to look ahead sufficiently. What we're trying to do with the Q function is we're trying to train a function that will tell us not only what's the reward in the next step, but what is the reward in all the steps to come from here, right? Of course, conditioned on all the decisions we make in the future, but that's this policy pi right here. I hope it's somewhat clear what a Q function is. Interestingly, we can take the same network architecture for this. So what you would do naively is you would build a neural network where you say, okay, a Q function takes a state and an action, so I'll put those into a neural network, and then out comes this estimation of the reward, which we usually call Q. So the value Q is this estimation of the future reward if you take this action in this state. Now, the disadvantage here is that we have to call this neural network once for each action in every state that we're in. So that's like, if there's 10 actions, that's like 10 forward passes. What we could do is we could simply take the same neural network we had for our very initial policy method, and we use that, and we simply input the state, and we'll train it to output the Q for action 1, and the Q, for the state S and action 1, the Q for the state S and action 2, and so on. So there is going to be this kind of shared encoder, and then that is basically going to encode the state into a latent space and then classify for each of the actions how valuable this particular action would be in that state. So this here is called a deep Q network. Okay, it's a network that takes in a state and gives you back the Q value. Now the problem right here is here we said if we had a perfect Q function, a Q function that was always right, then the problem would be solved, because we could just ask the Q function what to do. Of course, we don't have a perfect Q function. We need to train it. So how do we train a Q function? And the answer is surprisingly simple. So what you want to do is you are in this state, and you want to estimate, right, what your Q value is. You want to train your Q network. What you can do is you can simply play an episode according to the Q function you have. And you'll maybe play this episode right here, right? Like you go here and you collect all of this reward. So this entire thing now goes into your data set. And then you have a sample. I was here in this state S. I took action 1, and I got in total 2090 as a reward. So that is going to be your labeled sample, right? Your labeled sample is going to be S. I was in S. I did A1, and now I then got 2090 reward. Cool. And in the next episode, so you're going on playing, and you maybe go down here, and then you get a next training example. I was in state S. So you keep restarting the episode so you can get into the same state multiple times. I performed A3, and I got only 100 reward. So that's another training sample. So these training samples right here, you can use to train your Q function. This is called online reinforcement learning. You play the game at the same time as you train your neural network, and you use that improved neural network to play more games. And with time, there is this well-known, there are theorems around Q learning that say if you do that iteratively, then your Q function will converge to the optimal Q functions under some assumptions, which are of course not given if this is a deep neural network, but who cares? Yeah. So formally, your Q function, as you can see right here, is going to be, and there is this Bellman recurrence kind of recurrence property of the Q function. So if I am in a state S and I'm wondering what is my Q of my state S and an action A, and I said with respect to a policy, which the star policy is going to be the policy where we always select the highest Q function. So we'll basically say we're in state S, we select action A, and after that, we'll just always select whatever the highest scoring action is, right? Like right now, action A might not be the highest scoring, but we'll take A right now, and after that, the highest scoring. That's Q star. It's a Q function conditioned on the policy where after we perform the first action, which is A, we'll take always the best one according to the Q function, right? That's right here. So we're in state S, we perform A, and S prime is going to be the state that we are going to. So we're in S, we perform A, we get to S prime. So in S prime, which is a function of your environment, we're always going to take the maximum action, and R is going to be the reward of the next step. So you can see this recurrence equation right here, that Q star can be framed in terms of Q star. So the Q star of this state is going to depend on the Q star of the next state. And you can use that fact, and you can prove that we've already done it basically. You can use that fact to now train your neural network. So your neural network loss function is going to be the following. It's going to say, look, this here is the Q function for state S and action A. And this is my neural network telling me how much that's worth. And this is the label, right? So here you have to think in terms of back classic supervised learning. This here is going to be your F of X, and this here is going to be your Y. And we'll take the squared loss between the two, except your input X is going to be which state am I in and which action am I taking, and your label is going to be bootstrapped by your own Q function. So your label is going to be the reward you got. Remember, this comes from a replay buffer. We already played that game, and we already know what happened after we performed this action, right? And what happened is we got this reward, and we got into this state. So we can simply ask our own Q function again, what's the best action to take in this state and what reward would we get? And then we have our label, right? So our label Y is going to be, I was pretty confused when I learned this the first time. So I'm going to assume some of you are confused as well. So your Q function is supposed to tell you what's going to be the reward from here until the end of the episode, okay? That you can decompose in the reward that you get from this very next action plus the sum from then, so t plus 1, until the end of the episode, okay? So t prime, so that's t prime equals t plus 1. All right, so it's pretty simple. The total reward from now until the end, you can decompose in the reward now plus the reward after that until the end. Now, this here, we know. We've played the episode. We know what happened. This here, we can simply ask our Q function again, because we also know what state we got into. And this, as you can see, is very much this, but just one step later. So we can simply ask our own Q function, which might be imperfect, right? But it's certainly a good guess. We say, okay, this reward from now should be equal to the reward we got plus whatever reward we get later. And yes, you might be astounded by the fact that we are using our own neural network, though be it with the parameters 1 time step ago. in order to produce our label, but that is exactly what these Q-learning theorems are about. They basically say, under some assumptions, if you do this and you iterate, then this will converge to the optimal Q function. So as you can see right here, this is the gradient of the loss. It's astounding that back then they still wrote down the gradient of the loss. Like almost no one does this now. You just say, put this into TensorFlow and go. Yeah, so they make some remarks here, namely that this algorithm is model free, right? There's no model of the environment. You simply learn a function that for each state tells you the Q value for each action. That's all. Everything that all the logic needs to be within the neural network itself. So that's pretty cool. And they say it's also off policy. It learns about the greedy strategy while following a behavior distribution that ensures adequate exploration of the state space. So while training, they do this epsilon greedy strategy that follows the greedy strategy, which is where you always take the maximum, with 1 minus epsilon selects a random action with probability epsilon. So while you do your experience, you follow your Q function. You always ask the Q function, what's the best thing to do right here? But that gets you into too much of exploitation. So in epsilon amount of time, you want to do a bit of exploration and just take a random action. All right, so that's basically the algorithm. So the algorithm is right here, and they have some tricks to get it to work. And the biggest trick they got it to work is the so-called replay buffer, this experience replay. Because what happens if you play a game of Atari, right, of Pong specifically, then you have this, and you're here, and your opponent is here, and the ball is here. And in the next frame, you are here again. Your opponent might be a bit up, and the ball is here, okay? And so on. So these samples here, they are all very, very correlated, right? The ones after another, especially if you now build mini batch, let's say your mini batch size is 2, this mini batch has almost no variability in it. So if I do something like batch norm or whatnot, this will be like terrible because these data samples are correlated. And in supervised learning, we make a pretty big deal out of, shuffling our data set and all of the data points being IID and so on. So what they say is, rather than using the data samples as we collect them, we put them into a big buffer, a big replay buffer. And from that replay buffer, we basically sample at random. Okay, so that means that, some samples can be used multiple times. Other samples can be never sampled because there is a fixed size, and the new ones will always kick out the oldest ones. So some samples might not be used. Some samples might be used twice or 3 times. We can also learn, 4 times as fast as we sample, and then every sample on average will be used 4 times. So this experience replay proved very, very important for this algorithm to work. That's why they say deep Q learning with experience replay. So they have this replay memory D right here to capacity N. And you initialize your Q function with random weights, as you do with a neural network. And then you play these episodes. For each episode, you start out with S1, the state 1, and you do pre-processing. So in pre-process, they have some more tricks where they downscale the image. They concatenate 4 images in a row because sometimes in Atari you get these flicker things, and also if you concatenate 4 things in a row, you, for example, can tell in which direction the ball is moving and so on. So you give a little bit of history. So one sample technically would be 4 frames. They also do sticky actions and so on. All of these things that you can find today in these emulators that are almost default now, like sticky actions, they invented right here. So for the time steps within the episode, with probability epsilon, select a random action. Otherwise, just ask your Q function, what should I do right here? Give me the best action in this particular state. Then you would execute that action and observe a reward and the next state, so the next image right here. you would set the next state to this transition. Okay, so in the state there can be more, as I said, there can be more than the image, like the previous state and the action you took. But right here, I believe it's like purely the current last 4 frames. And then you store that transition in the replay buffer. After that, you sample a random mini batch of transitions from the replay buffer. So here you can see this here is where we decorrelate the inputs, because if we simply were to use our last transition for learning, then we would run into a problem. But right here, we sample from that replay buffer. So this is going to be your input. This is going to be your X for your supervised learning of the deep neural network. What's going to be your, without the reward, of course. What's going to be your Y? Your Y, if you're at the end of the episode, it's simply the reward that you got, because there's no more reward coming. However, if you're not at the end, it's the reward that you got from this last step, plus all of the reward that you're going to get in the future. Now, you aren't in the future yet, but you can ask yourself, you can ask your Q function what that reward is most likely going to be. If your Q function gets better, then this estimate gets better, then your labels get better, then your Q function gets better, and so on in a big circle. And then you perform a gradient descent step on this L2 loss between the label and your prediction. Note that there, if you are in a deep learning framework, there is like a stop gradient on this label right here. So the backpropagation only happens with respect to this right here, which makes sense, right? So this is your X, this is your input, and f of X is usually what we backpropagate into. Okay, there's no notion yet of like a second Q network and so on, which proved very valuable in the future of this paper. This paper simply applied kind of the most basic version of this, and they simply got it to work. They just got deep neural networks to work with reinforcement learning, and yeah, there's a big chance that this was due to this experience replay, which I believe they did not invent. I mean, this has of course been around before, but they were the ones to realize and combine and do that. It's also pretty interesting, the neural network that they actually used was like super duper small. The input to the neural network consists of 84 by 84 by 4 image produced by this. So this is the pre-processing. The first hidden layer convolves 16 8 by 8 filters with stride 4 with the input image and applies the rectifier nonlinearity, so the ReLU. The second hidden layer convolves 32 4 by 4 filters with stride 2, again followed by rectifier nonlinearity. The final hidden layer is fully connected and consists of 256 rectifier units. The output layer is a fully connected linear layer with single output for each valid action. Number of valid actions is varied between 4 and 18 on the games we considered. Okay, so you can see that neural network is pretty small. It's 2 conv layers, and as was in fashion back then, you had like big filters. So you know big filters from like AlexNet. You had big filters, but fewer than today. So today, the trend is more like deeper layers, more filters, but they are not as big. They're like 3 by 3 filters today only. Yeah, pretty interesting how they did it back then. Interesting also, no max pooling and so on. So pretty cool. And here they go into experiments. So they show that their average reward in these games is kind of noisy, but it improves over time, especially also if you look at the average Q of the max action, it continuously goes up during training. So this is really a successful training, especially this investigative experiment they did right here, where you can see one example of how the Q function, what the Q function says. Remember, the Q function gives us the whatever the future reward is going to be. Okay, and here we always look at the max action. So in this first frame, you can see this enemy had just appeared. And you can see that from here to here, there's a spike in the Q value because you can shoot enemies, and that gives you reward. This is already, so the enemy isn't shot yet. By the simple appearance of the enemy, the Q function also already jumps in value because it anticipates a future reward, right? Then the agent shoots, and you can see here the shot is about to land at the enemy, and that's when we're here. So now the Q function is very sure that in the future there's going to be a high reward. But then once the enemy is shot, then there is no more enemy to be shot. And the Q function drops drastically because it doesn't see a future reward as being as likely as at the beginning when there was this new enemy to be shot. So that's, pretty interesting, and you can see pretty directly that there is a correlation between what's happening in the game and this learned Q function. If you compare this to other methods, and they really say that these other methods, most of them have some kind of very special feature engineered, so their method just takes RGB, but the other methods recognize that, in these Atari games, most of the time, there are unique colors for the things. So, the enemies are all green, and they make unique channels for those green enemies, or they even have handcrafted object detectors and tell the algorithm where these objects are. So the comparison really isn't fair, yet the DQN outperform these others almost everywhere. And they also evaluated against a human. And I don't actually know. They just say an expert human. I have no idea. Maybe just put David Silver in front of a computer. Is okay, David, here you go. And you can what happened in Pong? Come on, David. But you can see there were still problems where the humans were vastly superior, and they mainly attribute this to the difficulty of the problem. And it could also be because, for example, in Breakout, there's this kind of the most famous example where the agent kind of figured out this strategy of shooting the ball, shooting a hole into this wall that you have to break, and then shooting the ball up here so the ball bounces up and down, and basically you win. From then on, you just watch the ball go, and the agent does nothing anymore. So this deep Q networks figured out that strategy, and you need to pull it off very precisely, which of course the computer can do very well. So it sometimes achieves these super high scores by pulling something off precisely. But in games where you have to plan ahead for longer, it kind of fails. And we know that this long planning was about to be a problem for years to come, and it's still not solved. So still, Go Explore is highly controversial that can solve these kind of long exploration games. And those are still games, right? So we are basically we are very much further than they were in this paper, but also we are basically nowhere yet. If I'm allowed to say that. So I enjoyed reading this paper. It's very well written if you somehow know how to think about reinforcement learning, this Q function, what the Q function means, and why you would learn it in this way. I find this is not super well described. This kind of requires a bit of a knowledge of, not of RL, but just of how to think of RL. But apart from this, everything else is written incredibly well, easy, straightforward. And this was just a nice work of its time, and I appreciate it for that. All right, I'll see you next time, and I appreciate your time too. Bye.